This is Advanced Algebra, Lesson 2.8, Fitting a Model to Data, Part 2. In Lesson 2.7, we looked at fitting a model to data, but we only involved two variables. We had a nice six-step process that we used. We're going to continue using that six-step process with the exception of the first step. When we model situations with more than two variables, we need to keep all but one of the independent variables constant and investigate separately the relationship with the dependent variable to each one of the independent variables. So that means if you have more than two variables, you're going to have to run more than one set of data. You'll be working with 2, 3, 4, depending on how many independent variables you have. We'll use the steps from the previous lessons, as I said, but instead of graphing, we're going to use the converse of the fundamental theorem of variation. I'll read that to you now. The first part is, if multiplying every x value of a function by c results in multiplying the corresponding y value by c to the power of n, then y varies directly as the nth power of x. That is, y equals k times x to the nth power. In part B, if multiplying every x value of a function by c results in dividing the corresponding y value by c to the power of n, then y varies inversely as the nth power of x. That is, y is equal to k divided by x to the power of n. In this first example, I would like to look at just a straight six-step process. We're only going to use two variables this time, but instead of using in step 1 of graphing, we're going to use the converse of the fundamental theorem of variation to determine how g varies with m, and then we'll write our variation equation for the situation. So please notice that g and m are both increasing. So if they're both increasing, we know that the variables have a direct relationship. So now we need to use the theorem of variation to help us decide how they're increasing. So let's take two data points. I'm going to look at 2 and 4. So the point 220 and 480. When I look at 2, I multiply 2 times 2 and I get 4. But when I multiply 20, I need to multiply 20 times 4 to get to 80. So as g doubles, m is being multiplied by 2 squared to get me, or 4, so it's being multiplied by 4. Let's take a look at a different set of data points. I'm going to use 220 again, but now I'm going to take 6, 180. So when I take 2, I'm tripling it to get to 6. But in order for 20 to get to 180, I'm not tripling it. I'm taking 20 to the third power, so I'm multiplying 20 times 9 to get to 180. So that tells me that m varies directly as the square of g, because when my independent variable is doubled or tripled, my value of m is squared. Is that value squared? Doubled squared would be times 4, or tripled squared would be times 9. So now that we've decided it's a direct squared variation, I'm going to insert my general equation, m equals k times g squared. Then I'm going to take a data point. I'm just going to start with an easy one, 1 and 5. Insert 1 in place of g and 5 in place of m, and solve for k. I get k equaling 5. And so then I can go ahead and write my specific equation, m equals 5 times g squared. Example 2 is going to look like it is very intense, but I'm going to start by reading the problem, and then I'm going to talk you through the process and show you that it's really not as intense as it appears. Alright, the problem. Consider the problem of determining the maximum weight that can be supported by a board. So that's what we're looking at. What's the maximum amount of weight that a board can hold? Okay. There are three quantities that influence the maximum weight. Let me read that again. The three quantities that influence the maximum weight m that a board can hold are the board's width, thickness, and distance between the supports. So the goal is to find an equation relating weight, thickness, and distance, or W, T, and D, and the dependent variable M. By keeping all but one independent variable constant, you can investigate separately the relationships between the dependent variable M and that independent variable. So as you look at how I've set this up, each time we are calculating weight. Okay? So you look at the three examples. Each one, the output or the dependent variable is our weight, or we're using the variable M. But if you look at the independent variable, in the first one we're going to look at width, second we're going to look at thickness, and the third we're going to look at distance between the supports. When I look at the width, I'm going to hold the other two variables, the thickness of my board and how far apart the supports are. I'm going to hold that constant for the experiment. When I go to measure thickness, I'm going to change the thickness of my board, but I'm going to hold the width of the board and the distance of the supports constant. And then with the third one, I'm going to change around my supports, but I am going to hold the thickness of the board and the width of the board constant. So when setting up this experiment to collect this data, all non-essential independent variables are held constant so that you could see how the independent variable that you're testing affects the weight, or M. So let's look at our first set of data. First, we hold the independent variables D and T constant by placing the supports at the ends of a 12-foot long, 1.5-inch thick board of different widths. We measure how much weight a board of a given width could support before it broke. See the data below. So I'm going to look at two data points to see how it's varying. So as I double my independent variable, 2 gets doubled to get to 4, I notice that my mass, or my M, is being doubled also. Let's take a look and see if that same thing happens when I triple my value. 2 double or tripled gets me to 6. 18 tripled gets me to 53. So as W triples, M is multiplied by 3. So M varies directly as W. Now when we looked at this, I said 18 triples and gets to 53. Now we know that 18 times 3 is not 53, but what we do know is that this is data, and we know that if I was going to triple it, if I'm looking at my increase 2 to 6 is triple, if it's a direct variation, it would be 18 times 3, which I know is 64, so 53 is off from there. But if it was going to be a direct squared relationship, I would have to take 18 times 9, and we know that that's nowhere near 53. So we know the relationship is a direct relationship, even though the data doesn't match perfectly, because when you're measuring things, it's not exact. So we have to allow for a little bit of a range of values there. So in this situation, we said M varies directly as W, so we know that that equation looks like M equals KW. Let's look at our first set of data. As you notice, I went through and I looked at my data right away, and I noticed that as my independent variable was increasing, so was my dependent variable. So I knew that I know that I'm going to have a direct relationship. But so I looked at that immediately, but let's go back and look and see what is happening in this situation. We're holding the independent variables D and T constant. So we're setting up on our experiment where we're having our supports 12 inches or 12 feet apart, and we know that the board that I'm going to be using is always going to be 1.5 inch thick. But the thing that's going to be changing in this experiment is the different widths of the board. So we measure how much weight a board of a given width could support before it breaks. So we're going to look at a set of data first. We're going to compare 218 and 436. Notice, as 2 doubles, I get to 4. But when I take 18, I double that, and I get to 36. So right there, both are being multiplied by 2. Let's look at the tripling piece. As 2 triples, I get to 6. As 18 triples, I don't quite triple it, but it's pretty close. Because I know that if I take a tripled squared, if I multiply 18 by 9, I know that's not close to 53. So I know that my relationship here is a direct variation. Now, it's data, so we know that it's not going to be perfect, and so that's why I could have the difference here of 53 instead of that 64 that I should have had. Let's look at our second set of data that was collected. In this situation, we held the distance between the supports constant at 12 feet again, but this time the width was held constant at 2 inches, and we varied the thickness of the board. So once again, as I look at the data, both the independent and the dependent variables are increasing. But now I need to see if it's a direct or a direct square relationship. So let's look at our data points, 2, 32, and 4, 128. As I double 2, I get to 4. As I double 32, I don't get to 128, so let's see if I can go 2 squared. So 32 times 2 squared will give me approximately 128. So therefore, I know that it's being multiplied by a direct square, but let's just check it again with another set of data. Let's go 232 and go 6 288. So as t triples, m is multiplied by 2 to the third, or 9. So m is, we checked it with another set of data, so m does vary directly as the square of t. So m is equal to kt squared. Now we have the third experiment that was held, and in this one they were investigating the distance between the supports. So the boards were chosen so the board stayed the same. It was 1.5 inches thick and 2 inches wide. And so they chose to vary the distance between the supports. And if you look at it this time, the independent variable is increasing, but the dependent variable is decreasing. So let's look at our data to see what happens. So 2, 106, and 453, as d doubles, m in this situation is being divided by 2. Let's take a look at another set of data. 2, 106, and 635. As 2 triples, it gets to 6. As 106 is divided by 3, we get approximately 35. So we know that we have an inverse relationship, so m varies inversely as d. Now that we've gone through and looked at each of the different relationships to the weight, or m, we now get to summarize our findings. This is the fun part. This is where we get to take each independent variable and insert it into our formula. So what we do is we look at the relationship. So here you can see I have it in bold. M varies directly as W. See it here over in this equation. And the square of t, as in this equation, while m varies inversely as d over in this equation. We express the relationship in a single formula. The independent variables have direct relationships with m are the numerators. So you can see I've put them on top of our division bar here, and we put d on the bottom because that has the inverse relationship. Now, one question that I often get is, what about k? Each of these is first independent, each of these individual equations here have a k also. What do I do with that? Well, essentially we're getting our own k, a new k for this formula that will have to be calculated if we want to move further. Right now we're just developing the formula at this point. We will, in lesson 2.9, figure out how to find our k for a joint variation, or a variation equation that has a combined variation. So our equation, after all of this, or our formula for this set of independent variables is going to be m equals k times w t squared all over d. This concludes lesson 2.8.